Okay, one of the things that it's in here in the notes and in the comments in the script that I didn't mention it yesterday, is that remember we assumed that the parameters for the arch model for the Garch model, the alpha 0, alpha 1, alpha 2, beta 0, beta 1, beta 2, all those are positive. Okay, so when we look at this table, this table where you have the values of the coefficients and you have the p-values for the hypothesis test that they know that the parameter is actually 0 when in fact it's different from 0. Okay, you know, the cases for the p-values for the model, the autoregressive moving average model, the ARMA model, or the model for the mean, those p-values, we interpret them exactly the same, the usual way, okay? So these p-values correspond to the null hypothesis that the parameter is 0 versus the alternative that is different from 0. Different from 0, okay? Except that when we look at the parameters for the Garch model, which are the omega, which is the alpha 0 in this case, and alpha 1, they have to be positive. So this p-value is in fact has to be divided by 2, because that p-value is a two-sided test, when in fact the only thing that makes sense in this case, for this particular case, we take the p-value that comes here and divide it by 2. That's the actual p-value, because the alternative in this case is that alpha, the null hypothesis alpha 0 equals 0, and the alternative is alpha 1 is greater than 0, and the null hypothesis for the alpha 1 will be alpha 1 equals 0, and the alternative hypothesis will be that alpha 1 is greater than 0. Okay, so we need to divide that p-value by 2. So in fact, the p-value for these two parameters, in this case for the alpha 1, is actually 0.02. Okay, that's one thing to remember. So if you see something here that's greater than 0.05, you have to divide it by 2 to know the actual p-value for that test. Okay. So that's one thing that I forgot to mention yesterday. Now, let's continue with the script, and now we're going to work with the industrial Dow Jones Industrial Average. That's the daily data. That's the daily returns from 20th of April 2006 through the 20th of April 2016. This package, which is the TTR package, is going to disappear sometime. So that's what you're going to get when you use it. You're going to get a message that this is going to be the instruction. This get Yahoo data is going to disappear. There are other alternatives, and it gives you here what the alternatives are to get stock data information. Okay, to get it directly into R. Okay, so you have to use a different package. It tells you here, warning, this is deprecated and will be removed in future release. And you need to use quant mode, get symbols instead of that get Yahoo data. Okay, so you can load, instead of using the TTR package, you can use the quant mode package and get the data. So the syntax for the get Yahoo data is you specify the name of the stock that you want to get the information from. In this case, is the Dow Jones Industrial Average, and that's starting. You specify the starting date as year, month, and day together without commas or spaces, and also the end date as year, the month, and date. And you specify also the frequency. It could be daily, it could be weekly, whatever. So I have now in DJ, I have this thing. If I look at what DJ has, DJ has the open price, the high, the low price, the closing price, and the volume that was traded in that day, during that day. So I'm going to use DJ Dow Jones closing price, Dow Jones closing. That's why they put C here. Is going to be the fourth column because that's 1, 2, 3, 4. That's the close price. Okay, the closing price is going to be the fourth column, and that's going to be my time series. That's how it looks. I have the date and I have the closing price for that particular day. Okay. The structure is already an XTS object, which is another type of time series object. XTS objects are like TS objects. They have different properties, slightly different properties. So there are different objects that are time series objects: the zoo, XTS, and TS objects. And as TS objects, as time series objects, they do have the information on the time series, whether the date and so on. Okay. Now look at the plot of VC. That's the Dow Jones closing price, daily prices, and well, you can see that there seems to be a trend. First, it seems to go down, then it goes up. So for sure, if we were to analyze the series and model it, we would need to take a difference because the series is obviously not stationary. And if we look at the autocorrelation function, it does not die right away. It's dying very, very slowly. So we need to difference the series. Now, the other thing that we are going to do with this type of data, we're going to be working with the logarithm. If we want to check with the Box-Cox, if I want to do the Box-Cox lambda for this time series for DJC, Dow Jones closing price. Oh, sorry. Oh, that's why I had an extra parentheses here that I hadn't seen. Okay. So I'm going to do this thing, Box-Cox lambda, and it gives me 1.72. So clearly it tells me that to square the data. With this type of data, which are closing prices, opening prices, maximum and minimum prices for stocks, and for any of this type of data, it's normal. It's the usual thing is to work with the logarithm because we're going to have to difference the series. No? So we're going to take the Dow Jones return. So we're going to be working with the returns, which we saw are the difference of the logarithms. Okay, so we'll work with the returns of the series, and that's the difference of the logarithm of Dow Jones closing price. Okay. Now let's look at the plot of the series, and now you can see that we have seen this in the first presentation in the class. We saw this thing, and as you can see, this fluctuates around the constant value. But what's important here is the volatility, right? And we can appreciate what we mentioned yesterday is that periods of high volatility are close together, and periods of low volatility are closer together. Now let's analyze the ACF and the PACF of the Dow Jones returns. Now we're working with the returns. Okay, and now that's ahead. That's the ACF2. That's the autocorrelation function of the returns. Now here, there's a couple of tentative models. We could think of an AR2 or an MA2, okay, because they only have two significant lags here. We'll start with an AR2 because of this PCA, the first two lags of the PACF are significant. So we'll start with an AR2 model. And we'll fit the ASARIMA with, for the Dow Jones returns, we'll fit the model one. I'm going to do this for model one, just in case I were to fit another from another model. It's an autoregressive of order 2. Okay. And that's the values of the parameters. Now, one of the things that we observe here is that the p-values tend to be small here. There's a few that are greater than 0.05 at the beginning, and then the rest are very small. And of course, we have departures from normality, because this curvature indicates that we do not have a normal distribution. Now, the constant term was not significant, so I can rerun this thing, and I said no constant equal true, because we already saw here that's not significant. Now I run the model again. Now we're going to look at the residuals from this model and look at the ACF and the PACF of the square of the residuals. Now, what's important here is that since we already saw that the series fluctuates around the single level, a constant level, and we already saw the volatility phenomena in the series, we don't worry too much about the fit for the first model that we did, because even though there's not a perfect fit, we know we're going to have to correct this thing, because what's important here is to model this volatility. Okay, so although the model is not perfect and have deviations from normality, now we'll continue and analyze the residuals squared to see if there is a gauge effect or an arch effect. I look at the ACF and PACF of the residuals, and there's a clear pattern here. Obviously, the square root of the residuals has a significant autocorrelation function, okay? And now we're going to look at the p-values of the square root of the residuals, and all are very small. All these p-values are very, very small. That tells us that the series has a gauge effect, okay, or an arch effect. Given that the p-values are very, very small, it's very unlikely that an arch model of order 1 or 2 will suffice. When we see p-values that small on the Young box statistic, and when we see a very strong pattern in the ACF of the squares of the residuals, that means that the model is going to be more complex than an arch model. And its standard practice will start with a gauge, the simplest one, which is a gauge 1-1. Okay. To fit the gauge 1-1 model, that for the Dow Jones returns, it's a gauge model. We'll use the function gauge fit that we used last class yesterday, and the model will be composed of two models. The ARMA model, I can eliminate the later one term there. That'll be the ARMA model with two parameters, and the gauge that we just fitted a few minutes ago, plus the gauge model 1-1 model, and we want the conditional distribution of the standard deviation. Remember that this is what these models are called, the arch and gauge, because they refer to conditional heteroscedasticity. So we are interested in the condition distribution for the standard deviations. The variance is the one that has a conditional, the variance is conditional on the time, actually. So we'll fit the model. Let's look at the summary. And let's look at the p-values. The AR2 doesn't come out to be significant in this case, okay? So the first thing we do before we analyze the model and see if it's a right model, we're going to eliminate the AR2 component, the second order autoregressive component. So we run it again as an ARMA 1.0, and then we analyze the results. We look at the summary. Now the parameters are all significant. Okay. Now the mean that was not significant when we just fitted the ARMA model, it is now significant. That's actually final. The AR1 term, and then this is alpha 0. This is let me write it down here. Omega is alpha 0. Alpha 1, that's alpha 1. Then beta 1 is beta 0, and this is beta 1. And these p-values have to be divided by 2. And we don't have to worry about that because they're very small, right? So we don't have to worry about that, but that the actual p-value is that those p-values divided by 2. So all the parameters turned out to be significant. Now we're going to look at the residuals of the model to see if the model is appropriate. Okay. So I'm going to plot the residuals. Remember that the structure of this model, if I look at the structure of this model of Dow Jones returns, instead of a dollar sign, what's separating the elements on this list for the first level are ampersands. Okay, so that's I need to use, and the residuals are here. These are the residuals. Let's say they're here. These are the residuals for the model. So I'm going to look at the residuals first. I plot the. We'll see now that there's another way to plot all this data. These are the residuals of the model. Okay. So we can observe that in these residuals, we still have high variability here, high variability there, and so on. And we'll look at the ACF and PACF of the residuals. The ACF and the PACF of these residuals, they don't look, there's no very strong pattern here. So in that sense, we think that there's not a big issue with the residuals because there's no pattern. Okay. If I saw a strong pattern here, that means that I have to go back and correct the model. Okay. I have to go back and correct the model, the gauge component of the model. But this seems to be okay. Most of the ACF values and the PACF are of the residuals of the gauge model, and combined with the ARMA model are non-significant. There's a few that are significant. Of course, I could always try to improve the model, right? I could say, well, what if I fit gauge 2-1 instead of a 1-1? Okay, maybe I can get an improvement of my residuals. Okay, I look at the summary, and looking at the values of my coefficients, I see now that omega is not significant. The other parameters are significant. So let's look at the residuals of this new model that we just fitted now. Okay, I'm going to run the structure again. These are the residuals, and this is the ACF. There's no big change in the ACF and the PACF of the residuals. If you compare this ACF and PACF with the previous one, we see that there is no big change. Okay, so there's no reason to complicate the model more. We can stick to the 1-1. We could also say, well, what if it's instead of a 1-1 and 1-2? I could do that. Look at the parameters, and now I can see that beta 2 is not significant. Okay, the p-value for beta 2 is 0.5. The p-value for the hypothesis that beta 2 is equal to 0 versus the alternative that it's greater than 0, it's 0.5. So definitely not significant. So I don't need that parameter. So I go back to the original model, to 1, 1, because the procedures didn't change much. Okay, so I'm drawing the model again, and I look at I have already seen my ACF and PACF residuals. But there's an easier way to get all these plots. There is a function, that the function plot, when it identifies that the object is going to plot is the result of a gauge fit, of a gauge model, together with an ARMA model, then the function plot has several alternatives. So it tells me here, do I want the time series? Do I want the plot of the time series? Do I want the plot of the conditional standard deviation? Or the plot of the series with two conditional standard deviations superimposed? Or the ACF of the observations and so on. So I can get all these plots from this plot command. What I have listed here are what I consider the most useful plots. Okay, this one is just the plot of the series. We already saw that. Okay, but I'll do it again. So I'll use the one, and then the conditional standard deviation. I'll do it one by one now, but you can do all of them right away with this thing. So I'll keep answering here. I'll do the times. That's the time series. We already saw that chart at the beginning, right? Then I'll plot number 2, which is the conditional standard deviation. And that is reflecting how the conditional standard deviation is behaving over time. Okay, that's a conditional standard deviation. Then the next one that I have here is 3, which is the series with two conditional standard deviations superimposed. That's number 3, sorry. That's number 3, yes. So this is actually more useful than just looking at the conditional standard deviation, because what I want to see here is if I essentially, if the model is reflecting the actual behavior of my returns, okay, of my returns of this for this time series, and I can analyze how these 2 times standard deviations compared with the series should definitely cover most of the actual values of the series. Okay, so here in gray, you can see the two conditional standard deviations. Okay, that's telling me that the model is actually reflecting very nicely the conditional heteroscedasticity of the model. The next one that is useful is to look, well, I can look at the residuals, which is 7. We already saw those. We saw them as the dot plot, right? As a scatter plot. And here it's joining the residuals with lines. Then the other plot that's useful is the standardized residuals, which is going to look, since they are standardized, now they're centered at 0, and they have roughly constant variance. And of course, we have some observations like these ones because of the changes in volatility, but that's the standardized residuals. So that's actually a more useful plot than the pure residuals. And we can also look at the ACF of the standardized residuals, which is the 10 here. And the ACF looks very good. The ACF of the standardized residuals shows that there's no significant autocorrelations in the residuals for the complete model, ARCH plus ARMA model. Then I can look at the ACF of the squared standardized residuals, which is option 11. And again, that's good news, because if this ACF of the squared of the standardized residuals gave a lot of significant autocorrelations, then that would mean that I need to go back and fit a different model. Okay, I need to correct the model. So this is an important diagnostic tool to see if I do not have any heteroscedasticity, conditional heteroscedasticity left that has not been captured by the complete model that I just feed now. I just feed it now. Okay. And the last one is the QQ plot, which is number 13, is the normal plot of the residuals. So again, it looks okay. There's some deviations here, but there's no such a strong curvature that like the one we saw in the original model, the original ARMA model. There's some deviation because we have some extreme observations there on the series. Okay, so those are the most useful charts. I can get all of them if I just run this whole thing and then a 0 to split that, right? To that function. If I want to get all of this, I just run this whole thing together and it gets all the plots. Okay, so now I got all these plots with one single instruction. Right? That was the last one that we got one by one, and here start the other plots. Okay. Now the other thing is that that is normally done with this series, and in particular, this is of interest for the people who work with financial time series like this, stock prices and stuff like that, is to calculate the volatility. Okay, the sigma of t conditional on t, t minus 1, t minus 2, and so on. For that, there is a function. I need to specify that it comes from the basics, from the basic R, because there's another volatility function that doesn't come from the basic R. Actually, if you try just volat, let me just volat equal volatility, then Dow Jones, that's the series, Dow Jones returns, that's the model, sorry. That's the series, Dow Jones returns the Gartz model, and the type of volatility that I want. I want to calculate the volatility for sigma, for the standard deviation. Type equal sigma. It's exactly what I have down there. If I say this, it'll give me an error, okay? Because this volatility function doesn't work with a Gartz model. If I want the volatility function to work, I need to use the volatility function from the basics package, which is, so I need to specify the name of the package, f basics, dot, period, colon, volatility, and how it works. Right? Now I've computed the volatility, and I'm going to join together. If I look at here, I'm going to say head, volat. So I have the values for volatility. This is a conditional volatility, conditional the standard deviation, conditional on time t. Time t is a time t minus 1, time t minus 2, time t minus 3, and so on. I'm going to join them together. The series, the Dow Jones returns with their volatility. And I'm going to validate the model is capturing, well, the volatility. So I can do this plot. The DJI volatility, which is this two series. I have two time series here. The first column is the Dow Jones returns. The second column is the volatility. So I take the data frame, and I use the TS plot so that it assumes that the object that I have there is a data frame that contains time series. And then I'm just going to use different colors. I'm going to use black for the Dow Jones returns and red for the volatility, conditional volatility. And that's the series, okay? So that's the red is the volatility, the conditional volatility of the series, which follows pretty much what we saw in the graph when we ran the plot command. Is essentially the standard deviation, the conditional standard deviation. Okay, so that's why it looks exactly the same. But if you wanted to work particularly with the volatility, this is a way to do it. And I can predict the future with the function predict. So I use predict and then specify the model, the number of periods ahead, and plot equal to, so it generates a plot. If I do my prediction, since I said plot, what did I say? It gave me an error. It's DJR. Sorry, DJ returns .g is the model. Okay. Okay, so you can see the returns are predicted as a constant value, right? And what matters here is the prediction for the conditional volatility. So it's increasing here. Okay. So that's a forecast function for this this Garch plus ARMA model. Okay. Are there any questions? No questions? Okay, so now I'm going to ask you to, I'm going to stop sharing and I'll split you in groups. And I want you to work on the following series. I want you to work on the Intel return series that's in Brightspace. Let me